this is B. Naresh, working as assistant professor in AEC department. And today's topic is principal operation of SCR, where SCR indication means silicon control rectifier. So in this session, we are going to observe what is the construction of silicon control rectifier and the working principle of silicon control rectifier, as well as the characteristics of silicon control rectifier. And before going to this session, we observed that some of the semiconductor materials like a PN junction diode, like PN diode, and we also observed the transistors. In the transistors, we observed a bipolar junction transistor as well as the field effect transistor. So in that also we observed that how to construct a normal PN junction diode and BJT transistor like NPN transistor or a PNP transistor. In the case of FET, we observed that a JFET as well as the MOSFET, metal oxide semiconductor field effect transistor. So in this case, and we'll discuss how to construct the silicon control rectifier and the behavior of the silicon control rectifier. And here, this silicon control rectifier is also constructed by using the two types of the materials like P-type material as well as the N-type material. And we know that in a P-type material, it contains the majority charge carriers are holes, and in N-type, the majority charge carriers are electrons. If you want to form the one junction and we are intersecting the two different materials, or in a semiconductor, one half is doped with P-type material, another half is doped with N-type material, then it is called as a PN junction. And based on this intersection of two different materials, it forms the depletion region nearby the junction, and this region is called as a space charge region, or it is also called as depletion region. And we know that in this P-type, the majority charge carriers are holes, and N-type, the majority charge carriers are electrons. And by using this principle, now we are going to construct the silicon control rectifier. It is also a formation of this P-type and N-type material. And again, before going to this section, again we are going to recall how this PN junction diode works. And to identify the behavior of this particular PN junction, we need to apply a amount of electric field. So means, or we need to apply some biasing for this PN junction. And with respect to this biasing, we have the two types of the biasing. We know that one is forward biasing. Another one, we have the reverse biasing. And when we can say that the forward biasing of PN junction diode, or when we can say that the reverse biasing of PN junction diode. So for this case, we know that let us consider this is P-type material and N-type material. When the P is connected to positive pole of the battery, and with respect to the negative pole means N is connected to negative pole of the battery, and then we can say that this particular PN junction diode works under the forward bias. And what happens when it is a forward bias means, and due to this applied electric field between the P-type and N-type material, the majority charge carriers are diffusing from the one junction to the another junction, means these holes are diffusing from the P region to the N region, and electrons are diffusing from the N region to the P region to form the conduction. And similarly, when the PN junction, the P-type material is connected to negative pole of the battery with respect to the positive pole of the battery, then we can say that this particular PN junction acts as a reverse bias. So under this reverse bias, it increases the depletion width, hence it does not allow the movement of the charge carriers from the one region to the other region to produce the conduction. Hence, there is no flow of conduction across the PN junction under the reverse bias. So by using these three principles and the construction and the working principle of this PN junction diode, forward bias as well as the reverse bias, now we are going to utilize this principle to identify the operation of silicon control rectifier. In this point, and this SCR, the silicon control layer, is a 4-layered semiconductor device that forms. So we have the two types of the materials. Already discussed that either it is a P-type material or a N-type material. Hence, it is a formation with either N-type and this is P-type. Again, N and a P-type materials. So two different materials, N-type and the P-type, and N-type and the P-type, are we can take like this: starts from the P-type material, then N again starts from the P-type and N. So these are the two different structures: NP-NP structure or P-NP-N structure. So based on this structure, it contains a 3 junctions. Those are represented with J1, J2 as well as the J3. So that is the reason we have the two types of the structures: NP-NP structure or PN-PN structure. Based on this constructing of the silicon control rectifier, it contains the 3 junctions. Those are represented with J1, J2 and J3. And based on this, so we have representation based on the construction. We have the 3 terminals. This SCR is a 3-terminal device. It is represented as, one is represented as gate, another one is the anode, another one is the cathode. These are the 3 terminals of SCR representation: gate, anode as well as the cathode. So most of the cases, this anode is represented as a positive polarity and the cathode is represented as a negative polarity. Now we are going to identify the structure. So for this case, if I am going to use this PNPN structure, so let us consider a piece of semiconductor. So let us consider a piece of semiconductor. And here we are going to connecting the 4 different materials. So this is a P-type material, and this is N-type material. Again, this is P and N. So this is called 4-layer structure. This is layer 1 and layer 2, layer 3 and layer 4. 4 layers. And already we discussed that the SCR is the 4-layered PNPN or NP-NPN structures, and it contains 3 junctions. Now we'll see what are the 3 junctions. So let us consider when it is called as a junction, means the intersection of the 2 different materials, that is like P-type and N-type material, is nothing but a formation of the junction. So this is the intersection of the P-type material and N-type material. Hence, this junction is represented as J1. And similarly, another layer, so layer 2 and layer 3 is formed at the nearby the one place, and this junction means the formation of the intersecting of this layer 2 and layer 3, and it is nothing but one junction. It is represented as a J. Similarly, the intersection of layer 3 and layer 4 are intersecting at one point, and this point is represented as J3. Hence, if you observe this, the structure of the silicon control rectifier, so otherwise, suppose if you take in the NP-NPN structure, means we need to start from N-type material. We are diffusing the N-type material. Then again, we are diffusing the P-type material. Then again, we are diffusing the N-type, and this is P-type. Then at this point, it is represented as layer 1. This is layer 2. And similarly, this is layer 3. And this is similarly layer 4. Now we need to find out what are the junctions are formed, means the intersection of this layer 1 material and a layer 2 material is acts as the junction 1, and the intersection of this layer 2 and a layer 3 is acts as a J2, and the intersection of layer 3 and the layer 4 is acts as a J3. So these are the three junctions either in a PNPN structure or NPNP structure. So hence the SCR is a 4-layered 3-junction device. It contains the 3 terminals. So one terminal is, so we have the 3 terminals. One is gate, another one is anode, and another one is cathode. So most of the cases anode is positive polarity and a cathode is a negative polarity. Based on this, we are going to place the electrodes, and those electrodes are acts as the terminals of the silicon control rectifier. So hence, for this P side J1 nearby to the J1, it is connected to one electrode. This electrode is represented as anode. Similarly, at the end of this layer 4, and we made one electrode, that electrode is represented as cathode. And similarly, now we are going to place gate. So gate, we need to place this terminal, gate terminal, to provide this gate terminal, and this gate is very near to the J3. So hence this is represented as gate terminal. So similarly, we can also represent for NPNP structure. But what about the structure? It contains the 3 terminals. One is represented as anode, one is represented as a cathode, and the gate. So if you observe this as construction or a structure, then this structure indicates that the silicon control rectifier is either PNPN structure or NPNP structure. It contains 4-layer device and a 3-junction formation, and it contains 3 terminals like anode, cathode, and gate. So this is the normal structure of the silicon control rectifier. So hence, here I am showing these points. The SCR contains 4-layer, already what we discussed. So PN structure with out of layers are referred as, so means out of layers means this is out of layer. So, and this is another out of layer. So it is represented as, so anode is a P type and the cathode is N type. Means here also here it is represented as anode and here it is represented as cathode. Then here it is represented as gate. So hence anode P type and cathode is N type. The control terminal of the SCR. So we need to control the flow of charge carriers or the allowing the conduction, that is controlled by the one electrode or the terminal, that is called as the gate, and it should be connected to the P layer located to the next cathode. So hence, so this is the P layer that should be next to cathode, hence it is represented as gate. So here also in a PNPN structure, the gate is connected to the P layer, means nearer to the cathode. So if you take in this NPNP structure, it is nearer to the cathode is containing the P type layer. So hence these are the points, and then from this either the PNPN structure or NPNP structure, we have the 3 types of the junctions. Those are represented by J1, J2 and J3. Hence it is represented with the 3 junctions J1, J2 and J3. Then so this is a normal construction. Then I'm going to show the symbolic representation. This is the symbolic representation of SCR. So this is the symbol for SCR. And in the symbol also, we are showing 3 terminals. One is nearer to the P1 layer, anode. One is nearer to the N2 layer, that is cathode. And this is a gate terminal. So here PN and PN, I define the differently. P1 and 1 like the P2 and N2. Gate is very near to the cathode and it is formed with a P-type material, and again, that is represented as a gate terminal with respect to the intersection of each and every layer. That layer is represented as the junction J1, J2 or a J3. Now by using this one, now we are going to observe the behavior of or a principle of silicon control rectifier. And to identify this behavior of the silicon control rectifier, we have the 2 analyses. One is either the load is connected in series with the anode, and The anode is always kept at a higher potential than the cathode. So these are the conditions to allow the conduction in a silicon control rectifier. The anode is always kept at a higher potential than the cathode. Then, and this principle of SCR, we have the two different conditions. One is when the gate is open or when the gate is positive with respect to the cathode. So why we'll discuss later why always the gate is a positive with respect to the cathode. So these are the two different options. So that is the reason the SCR is a control by with respect to the gate terminal ends. And we are going to observe the principle or the working condition of the silicon control rectifier with either the gate terminal is open or gate is a biased with a positive potential with respect to the cathode gate. So we'll discuss in detail what happens when gate is open and what happens when the gate is made with a positive with respect to the cathode terminal. So for this case, so first I consider when the gate is open. So in this case, when the gate is open, again we have the two options. One is a forward biasing or a reverse biasing. We have the two options. One is forward biasing, another one is reverse biasing. Now, suppose if I consider the PNPN structure, let us take this is P1 and N1, P2 and N2. And we know that the anode is made with a cathode, a positive potential, hence P1 side. Let us take this is anode. And the other out of surface, it is represented as one terminal is cathode. And near to the cathode and for the P2, a electrode is represented as gate. Now let us consider, and this is the junction J1, J2 and J3. Suppose now I'm going to apply. So we have the two options. When the gate is open means none of the external force is applied between the gate and the cathode. Hence, the gate is open. Simply, we are not applying any electric field through the gate terminal. That is called as the gate is open. Now we'll see what happens when a gate is open with respect to this biasing voltages here, either in a forward biasing voltage or a reverse biasing voltage. Now we'll see what is the forward bias means. Already we know that the forward biasing means, so let us consider for the PN junction. If it is a PN junction, this is the P type material and N type material. When a P is connected to positive pole with respect to the cathode or N type material, then we can say that this PN junction diode is acts as a forward bias. So hence, now this anode is made with the positive pole of the battery with respect to the cathode. And this is the negative pole. And this is called as when the gate is open under the forward biasing voltage between the anode and the cathode. Now we'll see what happens due to the applied this electric field between the anode and the cathode. Now we'll see what happens in the junction. Suppose if we consider a normal PN junction. So what happens in normal PN junction? This is the intersection of P type material and N type material. If P is connected with a positive pole with respect to the N pole, what happens? So this is the normal depletion space charge region. So when we apply the forward voltage, it decreases the depletion region. Hence, the movement of the diffusing the charge carrier concentration is increases from the P region to the N region or the N region to the P region to allow the conduction. So at this point, let us consider what happens in the J1, junction 1, what happens in the J2 and what happens in the J3. If you observe the J1 of P1 is connected to positive pole, hence we can say that the junction 1 is acts as a forward bias. So J1 is acts as a forward bias. If you consider the J2 means this is N1 with respect to this one, higher potential. Always we take a higher potential is anode compared with the cathode. And for this N1, we are applying the positive, means for N1, we are applying the positive pole. So hence, if for N-type material, if we apply the positive pole of the battery, then we can say that that particular junction is acts as a reverse bias. Hence, J2 is acts as a reverse bias. J2 is acts as a reverse bias. And if you observe the J3, and the J3 is intersecting from the P3 to P2 to N2, and for this one, so means P2 is connected to positive pole of the battery. If a P is connected to positive pole of the battery, we can say that that particular junction is acts as a forward bias. Hence, it is acts as J3 is also acts as forward bias. So N. So from this representation, if you are redrawing the internal operation with respect to this biasing voltages, what happens here? J1 and J3 is acts as a forward bias, and the J2 is acts as a reverse bias. So hence, I'm going to redraw in the structure. If it is, and this is the P1 junction and N1 junction, this is J1 junction, and this is P2, means N1. Let us take this is P2 and N2. Let us consider this is P2 and N2. But what happens in the J2? So J2 is acts as a reverse bias. Hence, the J2 is a reverse bias means, so depletion layer is increased. So this is the junction, means suppose this is now, what happens? So this type of depletion width is increases, and this junction is represented as a J2. So hence, so this is the junction P1, J1 is a forward bias, means it is a conducting state. J1 is a conducting state. J1 is acts as the on state. And J2 is acts as a reverse bias, means J2 is a non-conducting state. Hence, the state is represented as the off state. But J3 is again forward bias. So J3 is a forward bias, means that is state is represented as on state. So hence, but we need to allow the conduction. If electrons are repelling from, this is the anode and this is the cathode. The electrons are repelling from this cathode to anode, the current flowing direction from so this anode to cathode. So ends, but the current is flowing from this J1 to, means current is flowing from anode to cathode through the J1 to J3 junction. But in between, what happens here? J2 acts as a non-conducting state. Hence, it does not allow the movement of this anode current to the cathode side. While because of the J2 acts as a reverse bias. Hence, there is no conduction takes place across the SCR, even though if you are applying the forward conduction. And this state here, it is called as forward blocking state. So this state is called as a forward blocking state when gate is open, and even though if you are applying the forward bias voltage between the anode and the cathode, and due to the effect of J2 junction is a reverse bias and there is no movement of the charge from anode to cathode, hence the state is represented as forward blocking mode. So that is the reason. At this point, due to this forward blocking mode, the SCR state is represented as non-conducting state. Hence, the SCR is represented as cutoff state. Similarly, we will observe what happens when the gate is open, even though if you are applying the reverse bias voltage. Hence, for this case, in the previous case, we observed that when gate is open and we apply the forward biasing voltage. Now we are going to observe with respect to the gate is open and we need to apply the reverse voltage. So that is the reason. Again, I am going to take this PN structure and let us consider this is P1 and N1, P2, N2, and this is anode and this side is a cathode. And we have the three junctions J1, J2 and J3, and nearby this P2 terminal is represented as gate. Now I am going to apply, when gate is open, I am going to apply a reverse bias voltage. Now see what happens. So hence, anode reverse bias means how, when we can say that is a reverse bias, when a p type is connected to negative pole of the battery and n is connected to positive pole of the battery, now we can say that there is a reverse bias. Hence, so if anode is made with the negative pole of the battery with respect to the cathode, hence, and this cathode is connected to positive pole, and this is it. Now we can say that this is called as a reverse bias condition. Means reverse voltage we are passing through this towards anode and cathode. So now we'll see what happens. Now again the gate is open. Gate is open means here I am not applying the any biasing voltage between the gate and the cathode. Now we need to observe what happens between the junctions. Means if you observe the J1, so J1 means it contains the formation of P1 and N1. But for the P1 layer, we applying the negative pole of the battery. Hence, if the P1 is passing to negative pole of the battery, then we can say that that particular junction is acts as a reverse bias. So hence, so it is acts as a reverse bias. And similarly, J2, what happens in the J2? J2 is the formation of N1 and the P2. For N1, we are applying the negative voltage. Hence, when for a N-type material, if you are allowing a negative energy, then you can say that there is a forward bias. Hence, J2 is a forward bias. And similarly, we need to verify what happens for the J3. For a J3 is a formation of P2 and N2. For a P2, we are approaching the negative energy. Hence, again, the J3 is also acts as a reverse bias. So, from these points, we observe that J1 and the J3 is enters into the reverse bias mode, and the J2 is enters into the forward bias mode. And according to the semiconductor diode, so if it is forward bias, then that state is represented as a conducting state. Hence, this J2 state is represented as on state. And whenever the PN diode is acts under the reverse bias, we can say that that state is represented as non-conducting state. Hence, that state is represented as off state. So, from this representation, now I'm going to redraw the internal operation of this 4-layered SCR structure when the gate is open with a reverse bias voltage. So, what happens here? Let us consider this is the J1. But J1 is acts as the reverse bias. Hence, if it is a reverse bias means the depletion width is increases. Let us take this is the depletion width. And let us consider again this is P1 and N1. Let us take this is the P2. So, and now I'm going to consider this is one junction. So, this is the junction J2. So, and this is P2 material. And this is N2, and this junction is and J3. Now J1, but J2 is a forward bias, means it is a conducting. But J3 again, what happens? Now it is again enters into the reverse bias. Hence, the depletion width is increases. Hence, only the out of these three junctions, only the J2 is a forward bias. But J1 and the J3 is a reverse bias. If a J1 and the J3 is a reverse bias, there is no movement of anode current from the anode to the cathode. Hence, under this state also, we can state as the SCR is acts as a non-conducting state. So that is the reason. So when the gate is open and no voltage to the gate, we observe that only the J2 is a forward bias and the remaining J1 and the J3 is a reverse bias. Hence, due to this reverse bias of J1 and the J3, there is no movement of the charge carriers from the cathode to anode, and there is no flow of conduction, and there is no movement of the conduction from anode to the cathode. Hence, the state is also represented as cutoff state. So that is the reason. If you observe what happens when a gate is open, even though if you are applying the forward voltage or a reverse voltage or a forward bias or a reverse bias, the SCR is non-conducting. But we need to identify that when the SCR is enters into the conducting state. So that is the reason. If you want to allow the conduction across the SCR or to allow the current from the anode to cathode, Now we need to apply a biasing voltage between the gate and the cathode. So if you observe when a gate is open, in this case, what happens when a gate is open and a forward bias voltage is applied between the anode and the cathode, only the J2 is reverse bias. Now we need to allow all current from the anode to cathode. We need to identify that all the junctions to be forward bias. If all the junctions to be forward bias, then it easily allow the current from anode to cathode. Means the movement of the charge carriers are easily diffusing from the cathode to the anode. Hence, it allows the maximum conduction from the anode to cathode. To make this junction to be forward bias, J2 to be forward bias, now we need to identify which type of biasing is applied between the gate and the cathode. So if you observe this construction, the gate is a biased with, or a gate is connected across the P2 terminal. Hence, that is the reason in operation we observe that the gate is positive with respect to the cathode. So that is the reason. Now we are going to observe what happens when a gate is positive with respect to cathode, and while we are applying the forward bias voltage between the anode and the cathode. Hence, now we are going to make this gate is positive with respect to the cathode. For this case, let us consider, so this is P1 and N1, and this is P2 and N2. Let us take this is electrode anode, and this electrode is represented as cathode, and nearby this P2 one electrode is represented as gate. Now if you want to allow or to repel the charge carriers from the cathode to anode, and we know that always cathode is biased with a negative pole of the energy, hence anode is biased with the positive pole of the battery and the cathode is biased with the negative pole of the battery. But already we observed that when gate is open with respect to this forward bias and there is no SCR conduction, even though if you apply the reverse voltage also, when gate is open there is no conduction. Hence, to allow the conduction, now we are going to apply a forward bias voltage or a positive energy with respect to the cathode is passing through the gate. Now, a positive pole of the battery is connected to gate with respect to the cathode. So what happens under this condition? We have the three junctions J1, J2 and J3. With respect to this biasing voltage between the anode and the cathode, we know that J1 and J3 becomes forward bias. J1 and J3 becomes forward bias. And with respect to this biasing voltage between the gate and the cathode, J2 is also becomes forward bias. So hence J2 is also becomes forward bias. And from these biasing voltages, we observe that all the three junctions are forward bias. Hence, you can easily allow or diffusing the charge carriers from the cathode to anode. Hence, the anode current will be flows from anode to cathode. So under this condition, this state is represented as forward conducting state. Hence, here the SCR is acts as the conducting state. Hence, this state is called as forward conducting state or forward on state. It is also called as forward on state. So this is like with respect to the cathode. So from this, from the three representations, what we observed, gate is open. Under this, we observe the forward voltage as well as the reverse voltage. When gate is made with a positive, so we observe the three parameters. Now I'm going to observe the characteristics between the voltage, means anode voltage and anode current. That is, x-axis is represented as anode to cathode voltage and current is also represented as anode to cathode current. And what we observed, when a gate is open, even though if we apply the forward bias, we observe the forward blocking mode. And when the gate is open, if you apply the reverse bias volt, we observe that reverse blocking mode. In this case, in both the cases, when gate is open, the SCR is a non-conducting under the forward reverse biasing as well as the reverse biasing. Hence, under the forward biasing, it is called as forward blocking mode, or it is also forward off state. Under the reverse biasing, it is called as a reverse blocking or reverse off state. But when it is a conducting, when the gate is made with some positive voltage, then only SCR is a conducting, and this state is called as forward conducting state. So hence, and up to this point, where the gate is open, hence is like say the non-conducting state. Whenever the gate is made with a positive energy, then it is enters into conducting region. Hence, the current is increases rapidly. And when the gate is open, so this is gate is open reverse blocking mode, and up to this point, this is gate is open and a forward blocking mode, and this is gate is made with a positive with a forward conducting state. So these are the some characteristic parameters or observed with respect to the principal operation of silicon controlled rectifier. Hence, we identify these are the three modes of states. So what are the three modes we observe? Forward blocking mode, or it is also called as off state, and a forward conduction mode. This state is represented as on state. This state is represented as on state, and a reverse blocking mode. This state is called as off state. So how to observe this forward blocking mode? So in the forward blocking mode, the gate is open and a anode is biased with a positive pole and a cathode is biased with a negative pole. Under this condition, what happens? J1 and a J3 is a forward bias and a J2 is a reverse bias. Hence, here the state is called as SCR is acts as off state. Under this forward conduction or on state, here gate is biased with a positive energy. Under this condition, all the three junctions J1, J2 and J3 all the forward bias. Hence, it allows the maximum conduction from anode to cathode. And this state is represented as forward on state. Similarly, the reverse blocking mode, or it is also on state. Here, the gate is open and anode is connected to negative pole, cathode is connected to positive pole. Under this condition, we observe that J1 and J3 is acts as a reverse bias and J2 is only acts as a forward bias. Due to this, the reverse bias of J1 and J3, it does not allow the current from the anode to cathode. Hence, this state is also called as reverse blocking state, this reverse off state. So up to this point, today we observed the construction and principle of operation. We also identified the characteristics of the SCR. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.